Look at a couple new rules today. We're going to look at the first one is the natural exponential function. So the rule for the natural exponent function is the derivative of e to the x is e to the x. If you think about that, that's kind of crazy. That the derivative of e to the x is itself. That's for any exponential function with base e. Now, first of all, how do you know if a function is an exponential function? It's when the x is in the exponent, right? We've talked about that already. But we're looking specifically only at when the base is the natural base e. Okay, so we're not going to talk about why that is. I'm not going to do a proof of that. You're just going to buy that the derivative of e to the x is e to the x. Now, that doesn't make for a very interesting problem. I can't say like, hey, question number 1, find the derivative of e to the x. It's pretty darn easy. So the only way to make it sort of interesting is to see how it's used in chain rule when e to the x is the outer function, when e to the x may be an inner function. So when e to the x is involved in product rule. So that's what we're going to look at. Okay, so we're just going to look at how to use this rule to find the derivatives. So this again right here is chain rule. I would say the outer function is e to the x, and the inner function here is sine of x. So chain rule says to do the derivative, I do the derivative of the outer function while I recopy the inner. So the derivative of the outer is itself, right? E to the x is e to the x, and I recopy the inner, then times the derivative of the inner, and the inner function is sine, so the derivative of sine is cosine of x. Now, there's not any simplification we can do here. Typically, we write the cosine of x in front of the exponential. So there is our derivative. Here's more of the same. So the outer function is e to the x, and the inner function is anything that's in that exponent, right? That would be, if I took this function and plugged it into that function for x, I would arrive at that composition function. So the derivative of the outer, since the outer function is e to the x, it's just itself, and I recopy the inner when I do that, times the derivative of the inner. So once again, we typically just rewrite it as 2 times e to the 2x plus 3. I'm going to set a world record for this video, maybe. This is more of the same. The outer function is 3 e to the x. The inner function is 2x. So when I do the derivative of the outer, the derivative of e to the x is just e to the x. And if there's a constant in front of my function like 3, it just comes along for the ride. So the 3 comes along for the ride, and then e to the x is e to the x. Now, because we're doing chain rule, I recopy the inner function, then times the derivative of the inner function. So the derivative of 2x is 2. I can reorganize here and call it 6e to the 2x. That's a prime there. My hand kind of wigged out. I don't know what happened there. Let's move on. This now becomes product rule. So this one was product rule where this one wasn't. That's because this guy here doesn't have an x in it, the 3. It's just considered a constant that comes along for the ride. As soon as we put this thing that we're multiplying out in front by, as soon as we put an x in that, it now becomes product rule, where that's my first factor and that's my second factor. So I'm doing product rule here. So derivative of the first times recopy the second plus recopy the first times derivative of the second. Now when I do the derivative of this, that's our chain rule. The derivative of the outer is e to the 3x, so I recopy it, but then times the derivative of the inner, which is 3. I see this factor as 3 things times each other. So I'm going to rewrite it as f prime of x equals 2e to the 3x. I'm not going to distribute that 3. I'm just going to say it's 3 times 2x plus 3 times e to the 3x. And then we're looking for a common factor here. So I can common factor out an e to the 3x. So when I ignore the second term, if I take an e to the 3x out of that first part, I get a 2 left over. Whoops, that is not what I meant to do. Don't know where I am here. This was notes, but why is it not showing up? That's a disaster. Oh, I need to be in all notes. There we go. All right, so I'm going to common factor and I get a 2. That's the button I was looking for there. Now I can't undo it. Sweet. Okay, so then I have a 2 left. Now when I ignore the first guy and I common factor out in e to the 3x, I've got my plus 3 times 2x plus 3, and then now I will have to distribute and simplify. And I'm going to reorder as well. So when I multiply out the 3, I'm going to get 6x plus 9 plus 2 is plus 11. So there's my derivative. Let's move on to the next guy. Again, product rule. So I do the derivative of the first, recopy the second, plus recopy the first, times derivative of the second. So again, e to the 2x, if I pull it out on the side, the outer function is e to the x, the inner is 2x. So it's the derivative of the outer is e to the 2x, I recopy the inner, times derivative of the inner 2. So if I rearrange my multiplication, I typically write numbers first, then any x's, and then any exponentials. I'm looking for a common factor. They both have a 2 in common, they both have an x in common, they both have an e to the 2x in common. So the first term, everything factors out, so I get 1. In the second term, everything factors out except there's an x left behind. So you can write this as 2x times 1 plus x e to the 2x. You could distribute that 2x out if you like. It doesn't matter too much there. Okay, this one is going to be a rewrite to the 1/2 power. Now when we have a power raised to another power, we can simplify by multiplying the powers before we start. So it's going to be e to the 1/2 times 2x minus 6. I can distribute that 1/2. I haven't done any calculus yet. Now I'm here just from simplifying, and then it becomes that chain rule again. The derivative of e to any power is itself, then times the derivative of the inner, which is just a 1. So the derivative is e to the x minus 3. Okay, don't forget this rule right here. When I have a to the m to the n, it can be written as a to the m times n. All right, that's the rule we applied there. Let's do a quotient rule 1. So I do the derivative of the numerator, which is a chain rule. The derivative of the outer function is e to the x, so it's e to the x, but I recopy the inner, times derivative of the inner. So there's my derivative of my numerator, times recopying the denominator, minus recopy the numerator, times the derivative of the denominator, all over denominator squared. We start to simplify just like product rule with exponentials. Whoops. This will be 9x to the 4th on the bottom. Up top, I'm going to reorder each term. So I'm going to get a 15x squared e to the 5x minus 6x e to the 5x. So I'm going to get here, I can common factor out a 3x e to the 5x. I'll have a 5x minus 2 all over 9x to the 4th. That x can divide out with one of those x's on the bottom. So it's going to be 3e to the 5x times 5x minus 2 all over 9x cubed. Oh wait, I can simplify that, divides in, and get a 3x cubed. So that 3 would be a 1 there. Alright, so that's how you take the derivative of an exponential. Now we're going to look at the differentiation rule for the natural log of x. These are the inverses of exponentials. So a log function is whenever you have an x inside the log. This happens to be the log of base e, which we don't ever write that. The shorthand is the natural log. Typically, we write our logs with a base, but when it's base e, we're going to just write it as the natural log. So this derivative rule is only for the natural log. So the derivative of the natural log of x is 1 over x. The thing that freaks people out, did for me when I first saw it, I couldn't get past it, like I always kept writing it in the answer, is there's no natural log in the answer. So let's apply some. Again, by the way, it's not very interesting. I can't ask you a lot of questions unless I make them chain rules. So here the outer function is ln of x, and the inner function is 2x minus 3. So if I do the derivative of the outer is 1 over x, except instead of writing x, I have to recopy the inner function that's plugged into x, which is the 2x minus 3. Then times the derivative of the inner for chain rule, so that's going to be a 2. So we've got f prime of x equals 2 over 2x minus 3. Okay, so we're looking at the next one. Again, it's a chain rule. The outer function is ln of x. Your inner function is 3x squared plus 2x, some polynomial. So the derivative is the derivative of the outer. The derivative of ln of x is 1 over x, except I have to recopy what's been plugged into x, times derivative of the inner. Then when we multiply these, that just multiplies into the numerator. So I have a 6x plus 2 over 3x squared plus 2x. I guess I could factor the top. It doesn't matter that I can really factor it because nothing crosses off, but if you want, you can factor out a 2. You can factor out an x. There's our derivative. Again, more inner and outer function here, composition, so it's chain rule. The outer is ln of x again. The inner is cosine of x. So the derivative is 1 over x, but instead of x, I have to recopy the inner function, times the derivative of cosine, which is negative sine of x. So I multiply that into the numerator, get negative sine of x over cosine of x. Of course, I can use an identity, get negative tangent of x. Oops, sorry. I was looking for a time on here, but it's not working out. Okay, so this one is the outer function is ln of x. The inner function is 2x minus 4 to the 1/2, and that's going to be a chain rule on itself. So inside of that, we're going to have another inner function of 2x minus 4. So this inner function is really x to the 1/2. Now, the thing about this is with logs, which is really nice, this is like a double chain rule, but there's some properties of logarithms that will help us to avoid that. So I'm going to do a rewrite here. I've got the ln of 2x minus 4 to the 1/2. There's a property of logs that says, before we do the derivative, I can bring that 1/2 down. This is not power rule. Sometimes we can confuse it with power rule because we're bringing that power down. It's not. It's a property of logs. And now it makes it a much easier problem. I can do the derivative. 1/2 out front, when you multiply by a constant, it just comes along for the ride. Now I'm doing the derivative of this guy. That is a chain rule where the outer function is ln of x and the inner is 2x minus 4. So the derivative of the outer is 1 over x, except I recopy what's in there, the 2x minus 4, times the derivative of the inner, which is a 2. So now when I simplify this, I get 1 over 2x minus 4. What I did was when I multiplied, these 2's reduced out. Okay, now we're going to look at some calculator stuff. So how do you find the values of derivatives using the calculator? So for each of the functions below, find the value of f prime at the indicated value of x using the graphing calculator. Then determine if the function's increasing, decreasing, has a horizontal or has a vertical tangent. Give a reason for your answer. Okay, so These are functions that would be a little bit trickier to take the derivative of. It's like, product rules and quotient rules with chain rules in them, with log rules in them. So on a calculator active question, we don't want to be doing the derivative, then if they let us use our calculator, just do it on the calculator. So we're going back to our calculator camp here. So we're going to put in the function in y equals 3 e to the x times sine of x then I'm going to quit. And so we've got it plugged into y1. So we're going to go alpha f2, n derive is number 3. So d dx, because we're taking the derivative with respect to x, alpha f4 gives me y1. And then I want to say when x equals -2. So I'm evaluating the derivative at -2 here. So what we get is f prime of -2 is going to be equal to -0.538. And we're always rounding to the third decimal place on the test. Now, does that make f increasing or decreasing? So we're going to say that since f prime of -2 is less than 0, then f of x is decreasing at x equals -2. All right, so you just saw how to do that. My suggestion is to go into, oh no, you know what, I'll just do it with you. So let's go into y equals. I was going to let you just do these on your own. We're going to leave y1 where it is in case we have to come back to that function. We're going to now in y2 put in number 2. Oh, actually it's the same function, right? So I don't need to do that yet. So I can quit out of here. And now I can do the same thing, but now I want to evaluate it at 1. So that's where I use my second enter trick. And that brings up what I had typed previously. And I can go back and change my x value from -2 to 1. So I think if I hit a delete there, it'll get rid of it. And I can overtype the 1. All right, so I get f prime of 1 equals 11.268. So I'll say since f prime of 1 is bigger than 0, then f of x is increasing at x equals 1. All right, now we're going to go into y2 because we're doing a different function. So we'll leave that y1 there in case we have to come back to it later. y2, we're going to say, we're going to make our fraction with alpha f1. And we've got the natural log of the cosine of x over x squared. So now we're going to do second enter to recall what we have here, but we want to do, sorry, I got to tone down those click things. We want to get rid of y1 and put in y2. And we want to do it for x is pi over 3. So I'm going to set f prime of pi over 3 equals -0.372. Since f prime pi over 3 is less than 0, then f of x is decreasing at x equals pi over 3. We're going to skip this guy. This is a bad choice. We're not doing that one. All right, let's go into y equals. We'll go down to y3. Just want to get rid of these. They're bothering me. I'm weird. All right, so we're in y3 here, and we're going to go, E is what, second? Yeah. Tangent. So our n derives, so I'm going to go second, enter. We're now doing y3, I believe. Alpha f4 gets our functions, y3. And we're evaluating at 0. So we're going to say f prime of 0 equals 0.340. Since f prime of 0 is bigger than 0, then f of x is increasing at x equals 0. Last one. Did we already have that function in there? No. So we got to do a new function here. So y equals, I will put it in y4, 5 sine of ln of x. Close the natural log, close the sine, and then square it. Remember, that's what sine squared means. You're squaring it after the fact. So, yeah, I think I need to actually put parentheses around the sine as well. So I'm going to need another set of parentheses. So I'm going to go over here. Oh, wait. Second, that brings me all the way to the front, right? And then I can insert some parentheses. Oh, I didn't want to do it there. I want to do it after the 5. So I go here and second insert some parentheses. Now I want to jump back to the end. Delete that squared. Put in some parentheses there, and then square it. Okay, that was rough. Now I can copy, second enter. I want y4. Some calculator stuff. And this is at x equals 1. We should get 0. Hopefully I used my parentheses correctly. We get 0. Remember, when you get e to a big negative number, that really means 0. It's doing an approximation. We'll talk a little bit about what the calculator is doing when we're using n-derive, but n-derive is an approximation. So that's close enough to 0 where we're going to say we know that it's 0. So f prime of 1 equals 0. So we're going to say since f prime of 1 equals 0, then f of x has a horizontal tangent at x equals 1. Whoops, that's a t. At x equals 1. We don't know if it's a max or a min. We just know it's a horizontal tangent. It may be a max, it may be a min, it may be neither, because I don't know if the derivative is switching from positive to negative or negative to positive, or it's not switching at all. But we do know there's a horizontal tangent there. Okay? Now we're going to look at some word problems or applications. This is our first look at some applications with derivatives. All right, so take a second and read the top of that. I'm not going to read to you. Okay, so if you need to pause it, you pause it. So derivative means the rate at which some quantity is changing. If I give you a function that represents a quantity, the derivative is the rate at which that quantity is changing. So we're going to really look at that. What does f of 5 mean versus f prime of 5? Okay, we're going to look at it as what does it mean in a word problem. So the first one is talking about the number of people entering a concert is modeled by F. T is the number of hours after the gates are open. Find the values of F of 1/2 and F prime of 1/2. Using correct units, explain what each value represents. So we're going to really look at the difference between these two. When I plug 1/2 in to the original function, what do we get? Well, let's go to our y equals. We're going to do calculator active stuff here. Turn on my little spotlight guy. Did we already have this function plugged in? We did not. But I'm saving all these functions because on an FRQ on a test, you may need to come back to one of them, and it's nice to not have to type it in again. So 560e to the sine of x. Okay, hold on. My lights just turned off in my room again. Gotta get up. Walk around. All right. We're back. So we just plug that guy in, sine of x. Do I have it in there right? Okay. So then we're going to go back to our main screen. First, we want to just plug it in. So that's going to be alpha. I'm losing track of what's what here, but I think it's y5 at this point. And we want to plug in 1/2. So remember that little trick there. We're plugging 1/2 in, and we get 904.482. And that's going to represent, in the context problem, a 1/2 hour after the gates have opened. That's a D. 904 people have entered the concert. So after a 1/2 hour, that tells us how many people have come into the concert. Now we're going to figure out what f prime of 1/2 is, and more importantly, what it means. So we want to copy that guy and change it to a y5. And we want to do it for a 1/2 hour. All right, so we're getting 793.757. Did I round that correctly? Yes. What that means is a 1/2 hour into the concert, or after the gates have opened. So a 1/2 hour after people are entering the concert at a rate of 793 people per hour. So that's very important to note. F represents the straight quantity, people, and F prime is the rate of change of people. Okay, so it's very important to note that. F is after a 1/2 hour, how many people are in. F prime after a 1/2 hour is the rate of change of the people at that moment. And that's what derivative is. At that instant, I can say how it's changing. So what do I expect? Since it's per hour in units, right? I expect another, in the next hour, another 793 people to come in. That's what the rate kind of means. It makes like, it's how fast the thing is changing at that moment. All right? How many people have entered the concert 2 hours after the gates have opened? So they just want to know how many people are in the concert after 2 hours. That's going to be f of 2. You can pause and do it on your calculator. You can do y5 of 2. I'm not going to do that. You see how to do it. So you're going to go over here and do this y5 of 2. And when you're done, you can come back and see if your answer is right. And then what does that mean? Again, it means 2 hours after gates have opened. $1,390 people have entered the concert. Is the number of people entering increasing or decreasing at this time? So we're going to take the derivative, check the rate of change of people, and that will tell us if people are coming in or if people are leaving, if it's increasing or decreasing. So we're going to do the derivative of 2. So you can pause it and do this, d dx, blah, 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 evaluate it at 2. See if you get the answer I get. So the answer is negative 578.545. So that means that since f prime of 2 is less than 0, then the number of people, that's f, entering the concert (2 hours). Let me see. Entering the concert 2 hours. I got to put that in there. I don't want to say is yet. 2 hours after the gates have opened. Is decreasing the rate of 578 people per hour. All right, so let's move on to number 8. We're almost done here. After being poured into a cup, coffee cools so its temperature T is represented by that function, where little t is minutes and big T is degrees in Fahrenheit. What's the temperature of the coffee 5 minutes after it has been poured into the cup? So what we're looking for is T of 5, and that's just going to be its temperature. So you got to go over here to y equals. You got to plug in this function. Then you got to evaluate it at 5. Again, I'm going to tell you to pause it and do all that and see if you get the answer. Okay, so this is what you should get. And that means 5 minutes after the coffee is poured. Temperature is 79.029 degrees Fahrenheit. Is the temperature decreasing faster 1 minute after it's poured or 3 minutes after it is poured? So that means we want to find the derivative at 1 and the derivative at 3. So again, you're going to use your calculator to find that. You can pause it and see if you get the values I get. So I get negative 33.359 degrees Fahrenheit per minute. Remember, it's a rate. And then after 3 minutes, I have negative 12.272 degrees Fahrenheit per minute. So the temperature is decreasing faster 1 minute after the coffee is poured. Because, and here's the tricky part, technically negative 33 is a smaller number than negative 12, but we're talking about cooling, we're talking about the absolute value. Remember what this means. That means in the next minute, after 1 minute, in the next minute we expect to lose 33 degrees Fahrenheit because it's negative, so lose. After 3 minutes, in the next minute, we only expect to lose 12. So it's definitely cooling off faster at first. So we have to talk about why. How can we make that number bigger? The absolute value of the derivative at 1 is bigger than the absolute value than the derivative at 3. That means it's cooling off, because cooling off means negative, and we can't say it's bigger because technically negative is a bigger negative is a smaller number. But if we absolute value it, that's our way of getting around that. All right? Thank you.